Let's start with a really weird thought. What if the chair you're sitting on isn't completely solid? What if, on some deep fundamental level, it's also a ripple, a wave? Now, that sounds like something out of science fiction, but it's not. It's the absolutely mind-bending reality we're diving into today. The idea that solid particles can also behave like waves. A discovery that didn't just tweak physics, it completely rewrote the rulebook for reality itself. And this question right here gets straight to the point. What if that hard line we imagine between a solid thing and a spreading wave is, well, just not real? What if every single particle, from the tiniest electron to a massive baseball, has a secret, hidden, wave-like identity? It is a strange question for sure, but asking it is the first step into the bizarre world of quantum mechanics. So, the official physics term for this idea is a matter wave, but here's the key. Don't picture a wave in the ocean. As this definition points out, it's actually a wave of probability. Think of it like a map of possibilities, showing where a particle is most likely to show up. This one idea is a foundation of basically all modern physics.
Yet to really get why this was so revolutionary, we have to go back in time a bit and look at the way things used to be. Physics had this very rigid divide, a solid wall that was about to come crashing down.
See, in the old school view of physics, reality was sorted into two neat little boxes. On one side, you had waves, things like light or sound that spread out and carry energy, and on the other, you had particles, solid little billiard balls of matter, like electrons. An object was one or the other, period. There was no middle ground, no overlap, or so everyone thought. And then, the first crack appeared in that wall. Experiments showed that light, the textbook example of a perfect wave, could sometimes act like a particle, a little packet of energy. This wave-particle duality, as it's called, was a total bombshell. And it got a young physicist named Louis de Broglie thinking, if a wave can pretend to be a particle, could it also work the other way around? And that simple question led him to propose a kind of universal blueprint, what's now known as de Broglie's elegant hypothesis. And here it is, the whole idea, in one breathtakingly simple sentence from 1924. Every moving particle has an associated wavelength. Not just the tiny stuff either. He meant everything. A baseball flying through the air, a car driving down the street, even you just walking across the room. According to de Broglie, you are also, right now, a wave. He didn't just stop at the idea either. He actually wrote down the recipe for it. This is the de Broglie wavelength equation. And it might look simple, but this is one of the most profound statements in all of physics. It's a mathematical bridge that connects the particle world of momentum directly to the wave world of wavelength. So let's break this down real quick. Lambda on the left, that's the wavelength, the waviness of the object. And p on the right is its momentum. That's the particle part, its mass times its velocity. The crucial thing to see here is that they're inversely proportional. Think of it like a seesaw. The more momentum something has, the heavier or faster it is, the smaller and more squished down its wavelength becomes. Okay, so that's a brilliant and totally wild idea. But in science, an idea is just an idea until you can prove it. And for something this strange, seeing really is believing. It was time to put it to the test. And that proof came in 1927 with something called the Davisson-Germer experiment. It was pretty straightforward. They fired a beam of electrons, which are definitely particles, at a crystal of nickel. Now, you'd expect them to just scatter like tiny marbles hitting a wall, but that is not what happened. Instead, they saw this, an interference pattern. And that pattern is the telltale signature, the smoking gun, of one thing and one thing only, a wave. This was it, the definitive proof. They had caught a particle red-handed, acting like a wave, exactly like de Broglie's math said it would. And in that moment, his hypothesis went from being a crazy guess to being a fundamental pillar of our understanding of reality. And believe me, this isn't just some abstract piece of trivia for physicists. Let's talk about how this bizarre quantum idea went from a wild theory to building the actual technology we use every single day. I mean, the list of applications is huge. It's at the heart of the semiconductor physics that makes your phone work. It's crucial for research into quantum computing, but probably the most direct and powerful example of us using matter waves is the electron microscope. So why is this such a game changer? Well, any normal microscope is limited by the wavelength of light. You just can't see details that are smaller than the wave you're using to look at them. But an electron's matter wave can be made thousands of times shorter than a wave of visible light. A shorter wave lets you see ridiculously smaller things. And the result is just astounding. By treating electrons not as little bullets, but as the tiny waves de Broglie predicted, we can build microscopes that magnify things over 1,000,000 times. We can literally see individual atoms. The entire field of nanotechnology basically exists because we figured out how to harness the waviness of matter. So this brings us back to our quantum reality, and a very obvious question. If everything is fundamentally a wave, why doesn't the world around us look all, waving? And the answer is right there in de Broglie's equation. Remember that seesaw trade-off between momentum and wavelength? Well, an electron has almost no mass, so its wavelength is big enough to be noticeable on an atomic scale. But a baseball, it has so much mass, so much momentum, that its wavelength gets squashed down to a size that is fantastically, absurdly small. We're talking billions of times smaller than a single proton. The wave is still there, in theory, but it's so tiny it has absolutely no way of ever affecting our world. But what is this wave, really? Well, here's the final, weirdest twist. The modern view is that the particle isn't physically smeared out across the wave. Instead, the matter wave is a probability wave. The high points of the wave are just the places where you're most likely to find the particle if you go looking for it. It's a wave of pure potential, guiding the particle from behind the scenes. And that leads us to one last really deep question. We started this journey with a clear line between solid things and spreading waves. We found out they're just two sides of the same quantum coin. And then we find out that the wave side isn't even physical. It's just a wave of probability. So if the very foundation of our universe is governed not by concrete certainty, but by statistical chance, what does it truly mean for anything to be real?